And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to continue our study of non-normal data, but we're going to look at it in our studio, so that's always a good time. So today we're going to look at a couple different data sets. Most of them are going to be, well, basically all of them are going to be the agricultural data sets that are so ubiquitous in design and analysis of experiments, since that's effectively where statistics began, with a bunch of people walking around a field counting leaves or plants, or in this case, the number of worms on a given plant. We'll see in a minute what I'm talking about. Anyway, the idea here is that we have multiple types of response data that is definitely not normal. We have numbers that are bounded between 0 and 1. It doesn't look normal at all when you plot the histogram. We also have counts data, like as I mentioned, counting things, also really not going to look normal, and we have to find ways to approach this. So we're going to talk about two. We're going to use transformations, how to transform our data in order to make it look more normal, but you can't always do that. And sometimes you're going to have to rely on the generalized linear model, and that's what we're going to be using today, the GLM function in our studio. So let's go into that and see how it works. And welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. Today we're going to continue what we were doing in the last lecture, that is looking at non-normal data in designed experiments. In this case, though, we're going to have a lot more fun than last time. We're actually going to look at some real data sets in R and see what we can do to try to work with them. Again, the main things we're going to look at are going to be, one, can we transform our data to make it look more normal? And two, can we use a generalized linear model to fit to our data? Right? These are the two tools in our repertoire that we will be working with. There are other methods out there, but this is what we will focus on for the sake of these lectures. And I think that with these two tools in mind, you'll be able to get a lot done if you ever encounter non-normal data. So how do we do that? Well, let's jump into our studio and see what we can do. All right, so in the topic of non-normal data, well, first I'm going to load in here both the mass library and the aggredat library, or package that is, which is full of, well, aggredat is my favorite one for design of experiments because it has way too many experimental design data sets all coming from the agricultural sector, which is where a lot of statistics originated. But before we get there, I wanted to revisit the rabbit data set. So this rabbit data set is in the mass package in R. It's one that we looked at earlier in this course in one of the assignments, but it's a good example of data that is, first we have to transform it because, well, let's double check what this data looks like. Actually, we have to transform the dose because the dose needs to be a factor or an ordinal factor variable. So what we need to do is use transform, or actually what we can just do, since we're just transforming one of them, I'm just going to do it like this, lest I ruin the syntax of the transform function, as I often do. And we're going to point out that this is ordinal, an ordinal factor, though for our purposes today, it won't really matter too much. Because what I want to do is I want to plot the rabbit data here, the dose on the horizontal axis, and I want to create box plots for the response variable BP change. So when we stare at that, there's one thing we note right away. It's definitely not homogeneous. It does not have, the variance is definitely not homogeneous, right? We see extremely low variances when we have low doses, very big variances when we have higher doses. Now, as a result, we have to be careful when we would fit a linear model, right? Or using a ANOVA here on this data set. Instead, what we can do is we can try to transform it and see what happens. So what we could do is we can try a couple different types of transforms. As these are is a positive response, we can try standard transformations like the square root. Okay, maybe that makes it a little better. We could try a log. That might help a little bit more. If we consider, for example, Bartlett's test, what we can see is that, actually I have to remember the syntax of Bartlett's test, which, yeah, numerical vector, and then I think you need a group vector. So we'll just look at this manual page to make sure that I get it correct. Yeah, G is the group vector, or the group, the factor variable. So in this case, what I can do is I can say rabbit $BP change and rabbit $dose. And what we find is an absurdly small p-value saying that the variances, like we saw from the box plot itself, are not homogeneous. But what we can do is we can try to transform it. If we take that square root transformation, do we do better? Well, okay, the test statistic has decreased, but the p-value is still very significant. Let's try that log transform. And yeah, well, again, the test statistic has continued to decrease, so that's good, but we still have a very significant p-value, so I guess they're maybe slightly more homogeneous, but yeah, we would still reject the null hypothesis that our variances are homogeneous even after a log transform. So again, it's sometimes hard to figure out good ways to transform your data. In this case, I haven't even tested for normality. We're just looking at trying to transform to get homogeneous variances, but we can actually do some tests for normality. So the Kolmogorov-Smirnov test is a standard one that's built into R. There's also the Anderson-Darling test, which you can find in the AD-GOF test package. Those are two standard ways of testing for normality. So we can do this, for example. What we would want would be to have normal, I guess, well, we would want this to be normal for all levels of, say, the dose variable. So I can say, I should be able to, well, let's use subset. Let's do this properly, right? Rather than trying to do it on the line like this, we will say subset rabbit BP change, and we want to say rabbit dose is equal to, let's say, 6.25. So this command should take out only the data point where the dose is 6.25. And yeah, that's kind of a small data set, but we can always try to, well, okay, we have to do a couple things first. We have to scale it. This data set actually might be too small to test for normality, but I'm going to push ahead with it anyway because we've come this far. I might as well try and see what happens. We can use KS test to run the Kolmogorov-Smirnov test for normality. Well, it's for goodness of fit to any distribution. I'm going to tell it that I want a normal distribution by putting p-norm as the second argument. And in this case, well, it gets mad at me because there are ties, but gives me a very insignificant p-value. The Anderson-Darling test, I think, doesn't actually, which is AD test, by the way, and has the same syntax as the KS test. Well, that one's also going to give me a fairly large p-value. Now, in this case, I do think we do have quite a small data set, so it may not really capture what's going on here. But at least these are tests that you could use. If you had a larger data set, you can use KS test and AD test in order to, well, test for normality or any other distribution that you may want to test for. Regardless, what I also want to do is I want to show you another tool because, again, we can try to, well, actually, we could try to transform our data and test for normality after that just to see if it ruins it. I'm going to do that first and see what happens. All right, that made it even, I guess, well, even the test statistic dropped. So it's still very not significant, saying that it's close to a normal distribution. Note that I had to scale this because I'm testing it with respect to the standard normal distribution. So I have to center it by its mean, scale it by its variant, or I guess, standard deviation before we actually apply the test. Anyway, where were we going with this? Well, what we want to do is I want to go back and actually fit a simple one-way ANOVA model to this data. So I'm just going to call this model 0. And what we're going to do is we're going to say that BP change, lowercase c, is going to be a function of, well, the dose. And the data set is the rabbit data set. Now, again, we don't have homogeneous variance here. We can still look at the results of fitting this model, and yeah, we see significant difference, which we kind of saw anyway when we looked at the plot, the box plot, but it's always good to have a p-value associated with that. Now, what I wanted to do is look at, oh, there's a box cork. I didn't know that. But I'm looking for box Cox, not box cork. So box Cox here, which you can find in the mass library, along with the rabbit data, by the way, it will do the box Cox power transformation for a linear model. So this is something that we talked about in the previous lecture. I said that one of the ways that you can approach transforming your data is to try to take the response to a different power. So we tried square root. We tried log, which is kind of like the 0th power. Maybe there's a better power that we can choose. And what box Cox does is that it considers an entire range of different exponents, in this case from -2 to +2 at steps of 0.1. So it's going to try a lot of different exponents to see how that transforms our data and how it affects, I guess in this case, the log likelihood. So let's see what happens if we do this. What it wants, right, for this is it wants us to just give it a fitted model, which can come from either LM or AOV, our favorite little function for fitting ANOVA models. So let's see what happens. If we type in MD0, what do we get? We get a parabola. Yeah, so what's happening here is it's actually computing a log likelihood. And what it's finding is the maximum likelihood estimator for lambda. And it's giving it to us in a plot. And if we look closely here, what it's saying is two things. One is it's saying that I found a maximum likelihood estimator for lambda. It's a power that's ever so slightly bigger than 0. But if you also notice, it gives you a 95% confidence interval for that parameter lambda. In this case, that parameter lambda seems to include 0, and 0, remember, is the log transformation. So what it's telling us is that, well, actually the log transformation is a reasonable one to try. You could use this, for example, to see if the confidence interval contains 1. If the confidence interval contains 1, then it's kind of like saying there's really no reason to transform your data. In this case, though, it does seem to be saying that, yeah, we should probably transform our data if we want to take that approach to analyzing this. But again, in this data set, we do have continuous responses, even though the variances are not homogeneous. If we go back to the plot, which was here, what we see is that the box plots are fairly symmetric, and we only have, I forget, like 10 data points per box plot here. So as long as you don't see anything horribly skewed and you have a continuous response variable like change in blood pressure, the normal assumption is probably safe enough. But there will be times when the data sets you encounter are obviously not normal. The first one that I want to look at today is this Accorsi gray leaf spot data set that you can find in the Aggredat package. So what's this data set? Well, it is a multi-environment trial evaluating 36 maize genotypes in 9 locations. So right away you think, well, why would that not be normal? Well, it's all about the response, right? So in our response variable here, it should tell us what it is. Yes, the response variable is the percentage of leaf area affected by gray leaf spot, which I guess is a bad thing. It sounds like a bad thing. I don't know anything about this agriculture, but I don't like the sound of gray leaf spot within each experimental unit. So it's actually a fraction of a whole. So let's again use head to see what is going on here with this data set. All right, so here's what the data set looks like. And the response variable here is, well, quite peculiar in the sense that y here is, well, values that are very small. But why don't we try to, well, we can actually do a histogram, I guess may be the best way to do it. Or a density plot, whichever you prefer, but let's try this. And we'll say breaks is equal to 25. Okay, so yeah, if you see data that looks like that, it's definitely not normal. Maybe we can even break this out to like 50 and see if we get any. No, it's just really small and then slightly not as small. And then, yeah, so you can see that this data actually looks like it was very coarsely collected in the sense that you have very small number, a number around 0.1, maybe 0.2, 0.3, 4, no 5, and then there's a couple 6s, a couple 8s, and maybe a 0.9 for that highest value. So we definitely don't want to just use the standard AOV function to do this, but not packages. What we can do is we can use the GLM function. And in this case, what we'll want to do, I mean, it tells you kind of right in here what you want to do, but what we'd want to do, right, is use quasi-binomial. And that's what we talked about last time. We want to use a logistic regression as one possible way to analyze this data. But the logistic regression, the classic logistic regression, is going to be looking for values that are either 0 or 1, binary valued. In this case, we don't have binary values. So what we're going to do is we're going to use quasi-binomial, which allows us to extend the idea of logistic regression to values that lie on the interval between 0 and 1. Now, I'm just going to run the code that they provided us with, but we should also look at it to see what in the world they are trying to fit here, because we didn't actually talk about the factors involved. So we actually have a 36 level genotype factor. That's kind of high, right, for what we've seen in this course so far, but it can happen, right? We have 36 different levels. In this case, there are 9 different environments where this experiment is being conducted. I believe this experiment is complete in the sense that we have all possible combinations, which, yeah, 9 times 9 is 81, times 4 would be 30. Yep, that sounds exactly right. Except that we yeah, so we also have a replicate at 2 levels. So this entire data set was replicated, or this entire experiment was replicated twice. Now, look closely down here at the bottom how they set up this equation. What they say is that we want to test, well, the environment. That makes sense. We want to test the environmental factor. We want to test the genotype. And we also want to test, well, what's going on here, right? Here, what we have is we're actually saying replication inside. Am I getting that the right way? The replication is tested within, I think, the environmental factor. So if we actually run this, we get an error. Wonderful, because I didn't actually run the rest of their code where they defined this data set as dat. And then I don't think any of this other code is relevant since it's just for plotting purposes. So let's try that again. We run this and, well, we get a model fitted. And the summary, it's not going to be an ANOVA table right away, right? What we're getting is actually the fitted values, or the, not the fitted values, the estimated parameters for the linear model. So in this case, we're getting estimated parameters for all of our 36 genotypes. And we're getting, let's see if we get to the top, we have all of our environments, all of our genotypes, and we have the replication within the environment. So why did they write it this way? Well, here's the idea. When we replicate this experiment, we're not creating a new environment to replicate it in. So each of this environment variable takes on 9 levels. And I don't think they're going to tell us what all of these things mean, which is a little disappointing because I'd be curious to know what CM and GO and whatnot are. We'll probably have to look up their paper, I guess, if we really want to know, in the Journal of Agricultural Science, which is right here. But regardless, imagine that you're running your experiment in 9 different locations, and maybe one is dry and one is wet and one is sunny and whatever. Now, if you're going to replicate your experiment, what you end up doing is you end up using the exact same locations. You don't pick a new randomly selected sunny location and a new randomly selected dry location and a new randomly selected wet location. You use the exact same locations as before. So in this case, because we haven't changed the location, right? We're not randomly selecting a sunny location out of all the possible sunny locations. We're actually just using the same one twice for each replication. And with that, they have to consider the replication within the environment, because what it's really saying is, okay, I went back to site CM, whatever that means, and I replicated a second time. And on average, that second time, the response variable was minus 0.02, or the estimated coefficient on average here was minus 0.12, or 0.12 lower than before. Whereas in the case of environment GO, the coefficient actually went up. Now, none of these look significant. I mean, this one is, under 10%, but that's not really that exciting, especially considering all the significance tests that were done here. But that's one of the little subtleties that they do here. If we wanted to have replication be independent of environment, we would have to randomly select new equivalent places to run our test and not just replicate the experiment in the exact same location. So it's kind of a subtle point. Hopefully it makes sense why they did it that way. Anyway, I don't really want to look at all these silly coefficients because, I mean, yeah, great. You can find out that certain genotypes are more significant than genotype number 1 because we didn't change the contrast. So all of these are just comparing to the themselves to whatever genotype 1 is, which isn't the most interesting thing to see. What we'd want to do, let's see if they're going to have it in the code here. Yeah, no, oh, they do have it. Well, all right, we'll just do it. I believe we can type in ANOVA here to our, I think they fit it as GLM1. Yep, there we go. That looks nice. So here we can type in ANOVA again, but it's important to remember that things have changed here and we're no longer getting F-tests. In fact, we're not getting any tests at all, if you notice, and we'll talk about that in a second. But we do have things that look kind of familiar, right? We have our environment variable, 8 degrees of freedom, 9 minus 1. Genotype, which is 36 minus 1. We have environment times replication. Now, it's not 8 degrees of freedom, it's 9 because it's also including the full kind of replications in some sense within the environment. So whereas if we had replication as a separate variable here, it would have the interaction would have 8 degrees of freedom, but in this case it has 9. Now, what else is going on in this table? Well, we have these deviance values, right? Which, what I mentioned last time, this is coming from the log likelihood. And we have that kind of hidden in here. We also have these, I guess, residual deviances as well. And then we're getting out something that's going to look a lot like, I find this table kind of messy the way it's arranged. But ultimately, we're getting out something that's going to look a little bit like a test statistic, but we have to figure out what it is. So I think if we type in ANOVA.g, all right, we'll get there. Maybe not. I'm pretty sure there was an ANOVA GLM. Okay, it didn't want to autocomplete for me, but if you type ANOVA.glm, remember, because ANOVA itself is just a generic function that will apply to lots of different fitted models in R. If I say ANOVA.glm, I'm saying, tell me what happens for GLM. And what it says here is that we can actually include different types of statistical tests as well. And they even have a cstat.anova if you want to know more. But this is something that we didn't do prior. So if we instead tell it that I want to run a test, I want to run, say, a likelihood ratio test, then what happens? Well, now I get some p-values out. So we go back through all this stuff, and it actually computes a p-value. Note that it's a chi-squared test, not an f-test. And we find, at least in this case, that both the environment and the genotype are very significant. This interaction, so the replication is not, that's actually pretty good. It means that when we replicated it a second time, there wasn't any real significant difference than the first time we ran this experiment. Anyway, it is good to remember that you still have the same intuition about what's going on here, but instead of sum of squares, we have deviances, and instead of an f-test, we have a chi-squared test. Now, there are a couple other options here. Some of them I think are redundant. I'm pretty sure if you type in chi-square, you just get the exact same thing out. Yeah. My favorite, though, is what happens if you type in f. Because remember what I said before, the f-test is tied very closely to the normal distribution. We don't have a normal distribution. So what happens if I tell R to do an f-test? It didn't yell at me. Maybe there was an other version of the code I was using before, because I was pretty sure it was going to yell at me and be like, no, that's really stupid. You're not supposed to use an f-test, but for some reason it didn't. I'm a little disappointed, I have to say. Maybe it was capital A ANOVA that I used. I'm not sure if this one applies to GLMs. That was a real big letdown, and now it's recorded on video. I'm so disappointed. I thought somewhere in here it specifically said you probably don't want to use the f-test, but we included it anyway because technically, yeah, here it is. F-tests are not based on residual deviance in analysis of deviance table, which is a really, opaque way to say don't do f-test. But I guess you could do f-test because strictly speaking, you could fit a GLM with a Gaussian distribution, which is basically, I think, the same thing as a regular linear model. Maybe it uses maximum likelihood instead of least squares to solve, but it's the same thing, so it doesn't really matter. Anyway, don't do f-test, even though in this case, I think it kind of just gave us the same answer anyway. It did give us an f statistic. That's quite interesting. The key would be that we would want to do a chi-squared test, which you can do by just typing in LRT for likelihood ratio, or chi-squared for, chi-squared, or otherwise. Looks like there's a few others in here, like CP, which is probably Mallow's CP, but we won't worry about that for today's lecture. Anyway, that's more or less all I wanted to say about this data set. It's a good example of data that's really not normal, and there's no good way to transform this to get normal data. A classic way to approach this would be with logistic regression. I did want to point out before we're done that you could try different types of regression methods besides logistic regression. So if we inspect this quasi-binomial, there's one other thing that I wanted to point out, which is that you can give it a link function like I told you last time. Now, by default, we're using the logistic link function, which is just logit as for short. So this is just the default. But there are a few others that you can find in here. Specifically, there should be one called probit and one called quotient in here. So probit is going to be another type of generalized linear model for data that lies on the unit interval between 0 and 1. The logistic regression does, well, uses the logistic function, which looks like an S shape with exponential tails. The probit function uses the Gaussian CDF, which also looks, well, like an S shape, but in this case it has, I guess, Gaussian tails to it. Anyway, you're probably not going to see anything noticeably different if I fit this other model. I mean, okay, yeah, we get this giant thing here, but what I actually really want is just the ANOVA table. And yeah, once again, if I do a likelihood ratio test, I should get out, yeah, p-values that are both super significant for the two factors and really not significant for the replication within the environment. So yeah, in that case, I just wanted to point out that you can do these different things, but at least in this case, and very often I don't see a huge difference. So maybe somebody out there has seen differences when they use different link functions like logit versus probit. Personally, I never have, though I would be really interested if somebody has a good toy data set where you can do that. If you are reading the source code or the example code, I should say, for this leaf data set, you will notice that they fit another model here using something called Wiederburn, I guess. And if you look, I'll be honest, I'm not actually that familiar with this one, but if you see here what they have for what logit looks like, the Wiederburn looks like it's the same thing, but squared. So again, there's lots of different links that you can use to try to bring these things together. But I'm not going to go through more of them now. They also use generalized nonlinear models, which is a whole nother thing, which we're not going to talk about in this course. But if you're interested, you can go see the GNM package. And I guess looks like there's a section of a textbook or something that will tell you all about it if you want to know what those are. For today, though, what I'd like to do, though, is consider another type of non-normal data in a design experiment. Now, this data set is huge. This is, I mean, large for a designed experiment, right? Not so large if you're talking about big data, machine learning and that stuff. But for an experimental design, 1300 is pretty big. Now, in this case, we're counting webworms in a beet field. Great, after putting insecticide. So we want to know, well, does the insecticide kill a lot of worms or dissuade them from attacking our beet plants? In this case, we have a row and column factor, as we often do when we have agricultural experiments. Our response is a raw count now. We also have a block variable, a treatment variable, and it looks like a spray and a lead. Oh yes, this was the one where treatment is a 4-level factor, which is either, but it's actually a combination of two binary factors. The first binary factor being, did you spray it, yes or no, with insecticide? And the second is, did you, I guess, apply lead arsenate, which makes me really nervous to eat those beets. I gotta say, like, organic farming, come on. I mean, I don't know. I'm assuming lead arsenate is, well, it's not an organic molecule, but still makes me kind of nervous to eat beets now. I'm hoping that wherever this farm is, it's not one in Alberta. Anyway, let's look at the data. All right, so what do we get here? Well, we get our nice factors, our block, our row and our column, and our responses. So specifically, I want to look at, well, the responses and plot it once again as a histogram. Maybe we can say breaks is equal to whatever, 20. And yeah, that's what our data looks like. So in this case, I probably didn't need to go to 20. We could do like 6 or 10 even. Yeah, and you can see that this is once again very not normal. It's also discrete, right? So if I look at a summary of this, right, it's definitely not going to look normal, and it's also only going to take on discrete values, which will make it extremely hard to transform it. Now, as I mentioned, sometimes people do like to take a square root transformation. In this case, I'm not too optimistic that it will work because we are so close to, it looks like a Poisson with like a rate parameter that's extremely small. So I don't think taking a square root transformation is going to make this look any more normal, but we can try it anyway. Yeah, that doesn't really help. So we'll forget that and pretend we can't, well, not pretend, note that we can't actually do any useful transformations here. Oh, except for one transformation, which is we need to make sure that it knows that the, let's see if they do it in this code, so I don't have to type it out. What we want to do, right, is we want to make sure that the row and the columns, which they don't include in their GLM here. Okay, well, I'll just do it then. The row and the columns are 1, 2, 3, 4, whatever, which means that R is going to default to treating them as a numerical variable, but we actually want it to be a factor variable. So we have to say row is equal to factor row, and call is equal to factor call. All right, I guess we could think of them as ordinal since they're ordered, but it doesn't really matter. Let's see what happens. So again, we don't want to fit a linear model here, but what we can do is we can follow the example that they used. And they said, since this is counts data, right, we're no longer contained to the interval 0, 1. We now have raw integer counts. And so we use a Poisson distribution. In this case, actually, it's funny they used it in quotes. I was just going to say family Poisson, and the link defaults to log, but I wanted to put that in explicitly so you can see it when we get there. Anyway, let's see what we get from our summary. We're going to get, all right, some neat stuff here. So we have our, well, again, when I do the summary now, it's just going to spit out a bunch of estimated coefficients. So I get my block variables in alphabetical order here. So 10, 11, 12, 13, and then it goes to 2. We have the spray, which is a binary factor. We have lead, which is a binary factor, and we have the interaction term, also binary. So at the very least, these all seem to be significant. And at least for binary factors, it's kind of nice to look at them in this table because there's only 2 levels. So what you're seeing here is the difference. You're seeing the estimated difference between level yes and level no. And it looks like the answer is 1 fewer worm on average when you spray. For the lead, you're seeing the difference between yes lead and no lead. And what you're seeing here is that we lose about half a worm if we apply lead. And oddly enough, if they seem to interact in a positive way, which is that if you apply, well, we'd have to think about exactly what's going on there. That's a little bit different because of how the interaction term is actually working, right? The interaction term here is comparing when you see that it being positive, right? And that can be a little misleading because you might think to yourself, well, wait a minute, if it's positive, doesn't that mean that applying both is actually hurting my performance? I'm getting more worms than I would if I apply both. But you have to remember that here, when we're doing the interaction, what we're doing, right, is we are, how do we say this in words, right? When we do an interaction between 2 binary factors, we're basically comparing when they agree and when they disagree. So it's kind of like saying, well, if they're both equal to, if they both have the same value, like they're both not applied or they both are applied, versus the converse, which is if one is applied or one is not applied. So it's a little bit harder to interpret that one. It's not just saying what happens if I apply both of them. Anyway, more interestingly, the ANOVA table. And yep, of course, I forgot. I always am a little disappointed that it doesn't just do a likelihood ratio test by default. not sure why, but yeah, notice that we actually get some similar p-values to what we saw above. Like, for example, this one is 741, and this is 0.3, and I think we have those right there, 7, well, almost up to the same thing, and then we have our 0.03 there. The tests that are being run are slightly different, so you have to be a little bit careful. And note that the test statistic up here is coming from, well, the normal distribution, because we didn't do a quasi-Poisson, we just used a Poisson. So we use a normal distribution here to estimate the p-values for all of these estimated coefficients, or to compute the p-values for the estimated coefficients. Down here, we're doing a likelihood ratio test and using the asymptotic chi-squared statistic. So again, we're getting a different type of statistical test, but to a certain extent, they do agree. And once again, we have these deviances, which very much act like sums of squares, right? They have their degrees of freedom, they have some value. We ultimately transform them into a test statistic. In this case, we don't have, I forgot to mention this with the leaf data from before, we don't have a residual deviant in this case. I mean, we kind of do, I guess it's over here. What we have though is we're comparing also to the null model. Remember, like I said, when you have these deviances, you actually have a log likelihood ratio. So what you have is you have the model. I guess what we're testing for is the model with and without each of these factors within it. And we're looking at the change in the log likelihood ratio. And that's where our test statistics and ultimately our p-values are coming from here. Anyway, I'm a little disappointed they didn't include the row and column, because I want to see what happens if we include the row and column. In this data set, I don't think there's anything too profound about the way that they're writing this. They have the block as a separate factor that's not interacting with spray or lead, which are interacting with each other. I don't want that. So we could try this and go back to our ANOVA table. And what do we get? Well, we had a lot of rows, actually. That's interesting. I didn't actually look at the number of rows, but apparently it has quite, they didn't tell you, it just says row is row. Not the most enlightening documentation, but that's okay. Anyway, we have a lot of rows, we have a lot of columns, and we actually see some differences here. It's quite interesting, because then you might ask yourself, well, why? I mean, presumably the worms could hop from one plot to another. I think in this in the documentation, they kind of say, oh, we try to spread them out so that they don't do that. But, you know, I wouldn't be surprised if they did that. Before we move on to our final data set, I actually think it might be worth just looking at some of these, because if I see that row looks to be significant, then what I might want to do is plot the response variable with respect to the row and see what I get, which is really hard to interpret. But it looks like, okay, yeah, there's definitely some jumps there. I guess because we have 50 whatever blocks, or even more. Okay, so let's try column. Maybe that'll be a little bit more sensible to look at. Yeah, I guess these are also hard to interpret, again, because we're looking at these as Poisson counts data, and we're not looking at them as normal data. So it becomes a little bit harder to interpret the box plots, which is another reason, again, why we need a generalized linear model. Though, I'm going to do, well, I want to look at spray and lead before we're done, if I can type it correctly. Yeah, so there's the spray factor, and we can look at the box plots, and we have to remember, again, they're not normal, they're discrete, 0, 1, 2, 3, and so on. But it does appear that the yes column is a little bit lower than the no column. So yeah, maybe this thing is actually working, right? I mean, yeah, the significance tests have told us that there is a very significant result there, but it is still nice to be able to visualize this. Because if you look at the lead variable, it doesn't look obvious that it should be significant. I mean, there are more outliers here that are at like 9 worms versus only, I guess, 5 worms, but still, it's not evidently clear from the box plot. However, if you look at the ANOVA table, it's like super significant that, yeah, you should probably be rubbing your beets with lead to stop the worms from eating them. And then, well, feed them to people, I guess, who should hopefully wash them very, very thoroughly. I guess you peel beets, so as long as the lead isn't uptake, it doesn't go into the soil and get absorbed into the plant, it should be fine. Anyway, yeah, so that's an example of some Poisson data. One thing I did want to do before we're done, though, is go back and fit this model one more time, but with a quasi-Poisson to show you the difference. So if we do a quasi-Poisson, what we're doing is we're including a dispersion parameter, which allows for the variance to change. Because again, the Poisson distribution is very rigid. We don't have the flexibility to change the variance. And in this case, oh, we get all those silly columns in there. Oh, that's actually quite interesting. Some of the columns are NA, which makes me think that what's happening here is there's some confounding. So maybe that's why they didn't include the row and the column in their example. Let's try that. Okay, that looks better. That's actually quite interesting that they would include the row and the columns like that. I'll have to look into this later offline because I'm kind of curious now. But for the sake of our learning, right, let's just go back to the original model that had spray, lead, the interaction term, and the block term. Now, if I say quasi-Poisson, note that what it did here was set a dispersion parameter to be 1.25. So what that means is that it says, okay, we're going to spread out our data a little bit more. 1 would be no difference than regular Poisson. In this case, it's just increasing the variance ever so slightly, and we do get some differences in our significance. Notably, the interaction term now is slightly less significant. It wouldn't be rejected at our 5% threshold if we were rigid and only decided everything based on whether that number was above or below 5%. You probably don't want to do that in practice, but just to point out that it is less significant if we were to use that threshold. That's because in this case, we're now estimating a variance or a dispersion parameter, and that's changing things, including changing our normal distribution to a t distribution. And remember from Stats 101, when you have something that's normal, well, you have a normal distribution. If you estimate the variance, now you get a t distribution when you're trying to estimate both the mean and variance of something. So again, not critical, but just trying to point out some of the subtleties and things that will arise if you try to use the GLM function. I think if we do an ANOVA table, presumably we'll get, oh, of course, test is equal to LRT, which I may start writing one of these days when we're actually allowed to go out of the house again. And yeah, you get significant p-values that look almost identical to the ones up here. But again, I do want to emphasize up here, we're doing a t-test. Down here, we're doing an asymptotic chi-squared test. So the data size here is quite large. So I guess it's asymptotic enough to count, but it is good to just remember what tests you're doing and the fact that they're not strictly the same thing, even though they are testing almost the same hypothesis. All right, let's do one more data set before my voice gives out. The last data set I want to look at is goes back to Cochrane, our good friend who gave us Cochrane's theorem. And this is the Cochrane wireworms data. So yet another data set involving counting worms, which I guess is, well, some people might find it fun. Regardless, the idea is here we have wireworms that are being controlled by whatever a fumigants, fumigants. Okay. Wow, that was a really poor pronunciation. Okay, so they're fumigating, presumably to try to get rid of the wireworms. Man, I've done too many of these lectures. I can't speak anymore. Regardless, this is a Latin square design, and I like Latin square design, so that's why I wanted to include it. So again, let's look at the data and see what we get. There's so many Cochrane data sets. Look at this, Cochrane beat, Cochrane whatever. I don't want Cochrane beats, I want wireworms. In this case, I think we can just look at the entire data set because it's pretty small. It's not like the other one at 1300. In this case, we have our 5x5 Latin square, and we have a whole bunch of different treatments, which should take on 5 levels. They are, as in standard style, not going to tell us what those treatments are. It's just 5 different fumigants. Yeah. Documentation means we're going to have to go look up Cochrane's 1938 article. I'm not actually going to do that. We're just going to look at this as a Latin square design. Now, again, I always like to look at the actual data that we get out. So let's go here and let's plot a histogram of the Cochrane, and there are way too many Cochrane data sets. And of course, W is the last one. A histogram of the number of worms. And yeah, okay, it's still not normal, as is the theme for everything in this course. But we might be able to do some type of a transformation and see if it gets any better. So we could try a square root transformation on this. And in that case, okay, that doesn't necessarily look normal, but at least it's a little more symmetric. So just for fun, why don't we try looking at a goodness of fit test? I'm not going to use Kolmogorov-Smirnov because it's going to yell at me and tell me that I shouldn't have tied values. But we can do this, but we have to scale the whole thing first to make it standardize it, so that we can then compare it to the standard normal distribution. And we get, oh, well, that's interesting, p-value that is not significant, meaning that at least up to the Anderson-Darling test, after doing a square root transformation, the data could be sort of normal-ish. Remember, we're not saying that the data is normal, we're just saying that the Anderson-Darling test did not reject normality. Now, okay, I guess we're not. Oh, because SP. Man, I cannot spell today. Yeah, there's also Shapiro test, which I believe is the Shapiro-Wilk test for normality. Oh, I thought it was Wilkes. I guess it's Shapiro-Wilkes test or Shapiro-Wilk test. Regardless, this test is just for normality, so why don't we try it on our scaled data and see what happens just for fun. It is always a good time when you just run lots of random goodness of fit tests on a data set. Yeah, so actually it kind of passed. That's neat. I shouldn't doubt Cochrane. I say I shouldn't doubt Cochrane because if you notice, before we take the square root, we get a very significant p-value saying it's not normal. After the square root, it's actually not too far from normal. Granted, it is still discrete, but it's not as bad as it could have been. Now, I kind of had tainted knowledge here. I didn't run these tests a priori, but I did look at the sample code that they had down here, and you'll notice that they actually do a square root transform here, which is kind of neat. So I thought, well, there you go. There's an example of where you can actually use a transformation on Poisson data, and it's not unreasonable to try that. But we don't know exactly how it's going to fit to our model, so why don't we load our data in here and actually fit some models to it. Yeah, they have all the plots. So the first thing here, luckily they gave us a nice transformation code here where they create a new factor, row F and column F for factors, row and column factors. And the first model they fit here is actually just a classic ANOVA model, assuming the normal distribution. In this case, they do a square root transform. Notice that they add a +1 to move it away from 0. We can still test for significance of the treatment as well as look at the row and column factors as blocks. But the actual estimated parameters are going to be a little bit harder to interpret. I think they did this probably to make it look maybe more normal, because the square root of 0 is still 0. But yeah, that's the transform. I guess here this comes from Snedeker and Cochrane, two sort of famous guys. So I guess you can trust that they know what they're doing when it comes to transforming data. And yeah, it's kind of neat, right? We get, well, our row, our column factor, not significant, and we get some significance in our treatment factor. So always a good time when that happens. And we can claim that, yes, at least one of these treatments was more significant than the other. And the nice thing is that now we can actually do a post hoc Tukey test, which you can't do. Presumably you can't do in the GLM case, though. I haven't actually tried it. I assume it would cause a R to just spit an error out at me. But anyway, if we actually wanted to look at these treatments that, yes, I don't actually know what they're fumigating with, we can kind of scan through and try to find the most significant differences, which seem to be, well, these, oh, my mouse has disappeared. There it is, which seem to be these three, which are the comparing M, N, and O to K. So K seems to be, I guess, well, actually doing worse, right? Because the difference is positive. So M, N, and O, oh, but they have more worms. So K is doing better because we want a smaller number. We want to kill as many worms as possible. Yeah, that's an interesting sentence for a statistics course. But yes, kill as many worms as possible. And it looks like factor K is doing the best, though is not significantly different than factor P, apparently, at least with respect to the Tukey test. All right, so this was, again, the way that we can just transform our data in order to fit a classic ANOVA model, assuming the normal distribution, as we've done for this entire course. But again, it is counts data. We can use the Poisson distribution, as they say here, with the GLM function. And we have the exact same setup here, but now we have a Poisson distribution. And if we type in ANOVA, what do we get out? Well, we get out, well, I still don't get I always forget to do that. I want my test statistics. There we go. In this case, interestingly enough, the row actually does look significant. So that's an interesting difference. The treatment is still significant, a much, much smaller p-value in this case. And the column factor is not significant. So that's quite interesting. Makes me wonder, actually, what would happen if we tried a quasi-Poisson with, well, I don't think I need to tell it log link. I think it just defaults to log link. Ah, that's interesting. So now I used a quasi-Poisson family, and suddenly that significance is not so as significant. Now, to be a pedantic statistician for a second, we don't like to compare p-values and say that p-value is greater than that other p-value, because strictly speaking, the p-value, if we want to be a good Neyman-Pearson hypothesis testing type person, then strictly speaking, we would set a threshold. If our p-value is below it, we reject. If it's above it, we don't reject, and that's it. But you can't help but just notice that here, when I change to a quasi-Poisson, that the p-values are suddenly not as absurdly significant as they were before. So it is worth noting. And what it makes me want to do is actually go back. What I should have done is fit these as save these in two separate variables so that I can look at the summary. Because the summary is going to tell us where the significance lies. And here, again, these test statistics are all significant, but they're telling me that there's a significant difference between these factors and factor K, which is the default alphabetically. So again, it's always good to know what what are being tested when you see a p-value, right? It's always important. Oh, and apparently there's one row that seems to be a little bit different than the others according to our generalized linear model. Now, if I change this back to quasi-Poisson, I really want to see what the dispersion parameter it decides to fit is. So let's see what that is. In this case, yeah, the dispersion parameter is not absurdly large, but it is greater than 1, so that does change things a bit. It also changes our distribution to a t-distribution, which is another reason why we might be seeing less significant test statistics. All right, so we have those things done. One other thing I wanted to do was to look at the summary.lm for model 1. And this is going to be the estimated coefficients for the linear model. Now, it changed the position of everything, annoyingly enough, but we're still getting the same conclusion, which is that all of these factors seem to be doing better than K, the default control group, because of the way R does things alphabetically. And we still see that one of the rows actually does seem to have some marginal significance to it. So interestingly enough, though, we didn't see significance in the row factor, I think, in the ANOVA table, if I recall. No, yeah, we don't actually see that significance there, mainly because I guess one of them is a little bit significant, but not enough to account for that with respect to these 4 degrees of freedom. If we were to try to split this, though, we might be able to see where the significance lies if we had different types of contrasts. Right, so that's more or less everything that I wanted to say about these data sets. If you'll notice, well, when we fit this before, we didn't do any blocking. Now you can't do, so I can do blocking with AOV in the sense of using the error function, but I can't do that with the GLM function. By default, I would have to switch to the GLMER, which is a generalized linear mixed effects regression model. We're not going to cover that because the syntax is kind of annoying in my opinion, and it's just different than what we would have seen before. But in this case, what they're doing is they're including the row and the column factors as random effects, which is something that we talked about before that we'd be interested in doing. It's just that you have to use a more sophisticated R function if you want to actually do that for a generalized linear model. And, well, I don't really want to do that now. So in summary, what did we learn? Well, we learned that sometimes you have data that is not normal, and extremely not normal in the case of some of these data sets where there's no feasible way to transform it. If your data is kind of close to normal, well, yeah, maybe you can transform it. Like in the case of taking a square root transformation, it could get you there. And then you can just rely on all the nice normal distribution theory that we've been doing for the whole course, f-tests and all that great stuff. And yeah, you can just push ahead with that. And that's often, so people do like that because people feel comfortable with the normal distribution. The problem is that after you've done a transformation, interpreting the results can be a little bit trickier than before. And if you do some crazy transformation, it might just make the people looking at your report mad. But if you do something like a square root, that's usually standard enough. But of course, you can always use the generalized linear model. The generalized linear model is quite powerful. You have to know what type of family to use, because if we go back to GLM, you might notice that we did 2 today. We did binomial, and which is logistic regression, and we did Poisson for Poisson regression. But we can do gamma, we can do inverse Gaussian, we can do well, I guess there's not as many here, but there's also other things, like, for example, there's negative binomial regression, which appears in a different R package. So there's a lot of other types of models that you could fit, and you have to know what type of family, that is, what type of distribution you want to use to model your data before you proceed. And I almost forgot. We have one extra bonus material that I wanted to do, which is let's see if Box-Cox is going to find the square root transformation for our Poisson data or not. Because we can always try to just fit a model, ignoring the fact that our data is not normal at all. And yeah, we can actually do that. We don't want to do that because it's bad practice, but we could do that. We could look at our ANOVA table and we see that, well, nothing here looks very significant. The treatment is starting to tend towards a small p-value, but I mean, the sum of squares is bigger, but it's not great. However, we can always go to Box-Cox, apply it to model 0, and see what it tells us. And it actually seems to prefer something closer to a log transformation, it looks like, than a square root transformation. You can actually get out these numbers rather than just staring at this plot and trying to see what's going on. But yeah, in this case, it seems to like a log transformation. So maybe what we should do is try a log transformation and see what happens. Cool. Okay, so we get a pretty strongly significant p-value here for the treatment, but we don't see any significance in our row or our column. Now, of course, we can always look at summary.lm to see if there's any significant differences here. Of course, we still see not really any significance in that row anymore, though maybe there's still a very subtle signal there, but we still can detect very significant differences in our treatment. Furthermore, I suspect that if we go back up, let's just fly up to the top, back when I used the the Shapiro-Wilk test and the Anderson-Darling test, if we switch this to a log transformation, now I have to add 1 in this case, otherwise I'm going to get a bunch of zeros. And we get something that it's sort of like on the cusp of being rejected. A p-value that is slightly above 0.5 makes me a little nervous. Like maybe this data isn't quite normal. It's definitely like not normal, but it's as long as it's symmetric enough, we're kind of good to go. Anderson-Darling is not as excited about this data. Anyway, that was just one extra little bonus fact that I forgot to mention before, which is that we could use Box-Cox to tell us how we should transform our wireworms data, or we can listen to Snedeker and Cochrane, who are two smart people, or were two smart people. So that's perfectly a fine way to proceed as well. Like I said, with the Poisson distribution, people often like to take a square root, but you could try something else as well, right? No one's stopping you. There's a very much art to this, to try to figure out how exactly do I transform my data? How exactly do I fit, like what type of model should I fit? The kind of stuff that would drive like a very precise mathematician insane, because it's like, let's just try some transformations and see what happens. But ultimately, yeah, you got to just kind of try some transformations, see what happens. But regardless, that is more or less everything I want to talk about today. We'll have one more extra bonus lecture next week, and then we are, I think, on to the review and finishing this course. So I hope you stick around for the last final couple lectures, and I'll see you in those.